Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to have a good revision of the tests. Unfortunately, in the question statement, as you can see, we're going to determine the convergence or divergence based on our own assessment on what test is the most applicable for the given series. So no test is provided to us, so we don't know exactly which one we're using. So that means we should pick the best test to get to the conclusion. That should be the shortest way, if possible. So we have a set of guidelines. Let me just explain what those are to you. All right, I will also mention the items in the video. You will hear a lot me talking about this, but I want to have a quick run through before I hit the road. First of all, the very first thing to check is the end term approaching zero or not. So if you have the assessment that the end term an does not approach zero as n approaches infinity, that means that you should go in that direction, and if the limit is not zero, then the series diverges, you're done, you can go home, okay? So this is the very first thing to check. And the second thing to check is is the given infinite series a known series like geometric, P, or telescoping, or alternating series? Because if that's the case, we have a strategy for each type of known series. If the given series is not one of those, then can the integral test, root test, or the ratio test be applied? So integral test is when you think that you can integrate the n term of the infinite series from, let's say, 1 to infinity. So if you think that you can integrate that and get a result out of that, go ahead and apply the integral test. And root test and ratio test are generally applied to factorial, like terms involving factorials and exponentials. So if you think that things raised to the power of n, or you have some exponential terms and factorials existing in an, so go ahead and try one of those tests. If all fail, then think about whether you can compare the given infinite series to another known infinite series by using the direct comparison test or the limit comparison test. So follow these guidelines, and I'm sure that's going to be very, very helpful in determining convergence or divergence. So we have 4 exercises to go. Let's get started.
All right, let's start with part A. We have n over 2n squared plus 1. And let's go back and check, let's use the guidelines, in other words. So does the n-term test approach, n-term approach 0? So what if we have applied the n-term test? Well, I'm sorry, but n-term test doesn't apply here because the limit of this is equal to 0 because the top is order 1, the bottom is quadratic. Even if you apply the L'Hopital's rule, you can pause the video and you can work on this limit, but I can tell you that the limit is 0, so n-term test is hopeless, okay? So this is hopeless, okay? Cross mark. Is this series one of the special types, geometric, P, telescoping, or alternating? So let's check. Well, this is not a geometric series because it's not written as ratio raised to the power of n. Nope, not geometric. Not P series, definitely. Not telescoping, definitely, because you can't split that into the difference of 2 fractions, right? Alternating, no, because there's no alternating part. There's no -1 raised to the power of n type term in the description of the infinite series. So, cross mark-ish. This is not one of the known series. Can the integral test, the root test, or the ratio test be applied? Yes. In fact, the integral test can be applied perfectly because with the integration skills you have currently, you should be able to integrate x dx over 2x squared plus 1. Okay, let me just write the dx here. And this is a perfect application of the u substitution. You call the bottom u, And believe it or not, you can integrate this expression pretty quick. So yes, integral test can be applied. So I'm going to put a check mark here, okay? Can we apply the root test? Well, if you watch my earlier videos, root test is the most applicable when you have the terms raised to the power of n. I don't have any term raised to the power of n, so I don't think that root test is the best way to handle this problem. So I'm going to put a cross mark here. Cross mark and cross mark, okay? So how about the ratio test? Well, ratio test can be applicable as well, but we, again, try to use the ratio test for the cases where you have factorials and exponential terms. You can give it a try, you can apply, but the test may be inconclusive, like the root test. You can apply the root test, but the test, again, may result in inconclusiveness, so you don't want to go in that direction, okay? Here we go. So I'm going to put a cross mark here. I think the best one that we can go with is the integral test. Why don't we do the integral test here? Okay. So here we go. I'm going to call u to be the bottom, as I just said, right? So that du equals 4x dx, right? Okay. Let me handle the indefinite integral version of this first. So essentially x over 2x squared plus 1 dx is equal to, so you have x dx, so it's 1/4 du divided by u, and that is equal to 1/4 ln absolute value of u plus c, but I don't need to worry about the plus c part because I'm going to use this result towards evaluating the improper integral. So I can go back and say like 1 to infinity x over 2x squared plus 1 dx. Oh, by the way, let me just put the u back here. ln 2x squared plus 1. Okay, here we go. We have the integral ln 2x squared plus 1. I don't need to carry forward the absolute value because, in fact, 2x squared plus 1 is always positive, so I'm going to put a parentheses instead. Okay, and this is from 1 to infinity, but remember, this part is going to be written differently. This part is going to be written in the limiting sense. Okay, so what does that mean? We had several examples earlier. So limit as b approaches infinity, 1/4 ln 2x squared plus 1, but b plugged in, so b squared plus 1. Okay. That takes care of the upper limit plugged in the limiting sense, minus, I'm going to put the lower limit in, so 1/4 ln 2 times 1 squared plus 1, that is ln 3. Okay? So let's try to handle this limit. Well, ln function approaches infinity, especially when inside of ln approaches infinity. So regardless of this number, this limit is infinity. So when this limit is infinity in the integral test, then the infinite series is divergent. Okay. By the way, I didn't list the comparison tests here. We didn't check the forward condition, but we can also use the comparison tests to deduce the same thing. Okay, especially for this problem. Let me explain that to you. All right, so can we compare this infinite series to another infinite series that we know about its convergency? Okay, if there was no 1 here, right? If there was no 1, then this series would look like 1 over n. So, in other words, why don't we consider the series 1 over n? So this versus this, right? So this is my an, this is my bn. Okay, I can perfectly apply the limit comparison test, which is checking the limit of an over bn. Okay, here we go. N over 2n squared plus 1 divided by bn, but I'm going to flip that over. So n over 1. So at the top you have n squared, at the bottom you have 2n squared plus 1. Why don't we use the L'Hopital's rule? twice maybe, because top and the bottom have order 2, 2n, 4n, and in fact 1 time is enough because n's cancel, so this limit becomes 1/2, right? And 1/2 is less than 1, and the limit comparison test says that these two series converge or diverge at the same time. Okay. Well, what do we know about this infinite series? Well, it's a p series for p equals 1, and when we know that when p equals 1, the p series diverge. And y, by the way, is p1 because the power here is 1. So p series diverge when p equals 1. Because that's in fact a special case. We call this series to be a harmonic series. So this diverges, okay? So is this, okay? Okay, by using the limit comparison tests. Okay? So that's good because we applied the integral test and the limit comparison test, and in this case, two of them were perfectly applicable to prove the divergency of n over 2n squared plus 1, the infinite series n over 2n squared plus 1. Okay.